And we're going to look at a few different beautiful graphs, okay? And our learning goal is just become familiar with a few graphs that are not parabolas. We've been focusing a lot on the parabola, and that's actually a really good thing. It's not going away. There's so much of this course that goes back to a parabola, but we need to go a bit further than that, and we're going to look at other graphs that exist in this course that we should be getting more and more familiar with and recognizing a few features of them. Now, there's a lot of graphs here, so I'm going to go a bit quicker, but make sure you ask questions in class. All right? Okay, so first of all, I've got this graph that we've seen before, and I showed you this graph because it was like the graph about functions and relations, and obviously this one is a relation and not a function because it fails the vertical line test because it crosses the vertical line test twice, okay? Now, we can make it into a function, okay? If I square root both sides, I get y equals, and I do it properly, y equals plus or minus square root of x. Now, that is still not a function, but if I split it up, the plus bit, just the plus bit, and that's it there. And can you see what the graph looks like? It's just the positive bit of this sideways parabola, and it is a function because it only crosses once because we're missing this bit down here. Okay, so just something to really notice about. Sorry about my cough. I just realised I was recording. Okay, so and the negative one looks as expected. It's just that bottom bit as well. Okay, so and also it still is a function as well because it passes the vertical line test there. It only crosses once. Okay, so we can do a variety of things with graphs, and we need to become familiar when you see a square root in an unfamiliar place like here, and you go, oh, what happens if I square both sides? Oh yeah, that looks like that, and that's kind of like x equals y, it's kind of like y equals x squared, but not. Oh, that's right, it's a sideways parabola, okay? So have a play with things like that. All right, let's keep moving along. I want to introduce you, we've done a lot of y equals x squared, but what does x cubed look like? Well, here it is, okay? Now, I've put in a couple more cubics later on in the video, but essentially, most cubics will look like this. But this is a unique type of cubic where it has all three roots in at the origin, so it just goes up and down. Now, one thing that I want you to focus on is that it starts low here and it finishes high here. So it starts low and it finishes high, the positive one. The negative does the opposite, so the negative is here. It starts high and finishes low. Okay, so and I'm going to point out those features as we come along. So make sure you draw this one in your book as well. I'm going to get a bigger eraser. Okay, let's keep moving along. X to the 4. Now, x to the 4 looks just like a parabola, but it's just a bit fatter down here, okay? And the negative one goes in the same vein that a parabola would look like. What do you think y equals x to the 6 will look like? If you think it will look like a parabola, but even flatter, you're 100% correct, okay? So the higher the power, the deeper it goes here in the bottom bits as well. And the reason for that is that it actually has 4 roots down here. Whilst y equals x squared, it's a bit shallower, only has 2 roots, okay? So that makes the deepness of these graphs like, yeah. I don't even know what I'm trying to say, but hopefully you get it, okay? Hopefully you can see that it's different to y equals x squared, okay? Okay, now this is where we're starting to get into recognizing, and these are the kind of questions that HSC asks for. Look at this. This is a cubic, so it's something y equals x squared, da 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 da, okay? But it's in factor form. We've been able to factorize it, okay? And look at this, -3, -2, and +1, okay? Where are the roots of this graph? And remember, the roots are where it crosses what? The x-axis, so this axis down here, all right? Well, there's one at, this is -1. Oh, that's the opposite of +1. There's another one at +2. Oh, that's the opposite of -2. And there's another one at 3. Oh, that's the opposite of -3. So it actually works in the same way that we do our normal parabolas. When we get a parabola in factored form, we know that we go, therefore, roots at x equals 1 and -2. Once we have this in factored form, even though it's a cubic, we work in exactly the same way, okay? So something to recognize. Now, I'm going to bring in another cubic, and this will be, notice, this is a positive cubic. Why? It starts low, see, finishes high, okay? Starts low, finishes high, and it always will follow this type of flow where it goes up and down and up, right? Okay, let's look at another one. This is a negative cubic. How do I know this? By looking at the graph, I can see that it starts high, goes up and down. See how it follows the same sort of flow? And it finishes low. So it starts high, finishes low, okay? Now, I want to look at the roots because I've got this for a reason. Let's look at this one first. I expect there to be a root at -1. And it just so happens that there is. That's -1 there, and there is a root there. Now notice this. I'll put this in for a reason. See how we expect there to be a double root at -3. I mean at +3, which is the opposite of -3. And there's one there, okay? But notice that this power, okay, and it's an even power, means that that root is a turning point. Can you see? It's a turning point. Okay? And it's really important you start recognizing this. There are still 3 roots. There's just 2 here. Okay? And it causes it to turn. So, say we had another one. And I'll just go to make this up. +4 squared x -1. I know that this one crosses x-axis at 1, and I know that this one has a turning point at -4. Okay, so because of the power here, all right, and that's exactly what's happening with this. Now, this only happens if the power is even. So be aware of that. If the power is odd, it will cross it. It will just be like a deep sort of cross, sort of boom, just like we saw. I'm going to go back, like here. See how it crosses the x-axis, because that's to the 3, and it's sort of a deep sort of point of inflection. Okay. Okay, so we've done that. And like I said, I'm going to keep moving along. And let's go to circles. All right, so circles are written in this form. All right, x plus, I think it's h squared plus y plus k squared equals r squared. All right. If I square root this number, what do I get? And hopefully you say 3. Okay, plus or minus 3, it doesn't matter. What is the radius of this circle? What is the radius? It's 3. So the square root of this will give us the radius, okay? And that's why it's written in this form. Okay, so it's the radius squared. Okay. And this form, x squared, y squared, all right, and for them to be the same, in this course I don't think we go to ellipses, tells us that it's a circle. Okay. Now, a circle is not a function, all right, because it fails the vertical line test right there. Okay. So yeah, hopefully you can see that. Now, what's our h and k in this case? Well, there's nothing else here or here, so that means that h equals 0 and k equals 0, which gives us the coordinates of the center of the circle. So that means it's going to be 0, 0. So the coordinate that's with x gives us the x coordinate, and the opposite coordinate, I'm going to look at it more in the next slide, gives us the y coordinate. All I want to know is that this one, because it looks just like that, it will have the center of the circle is at the origin, which is 0, 0. Okay, I'm going to explain this a bit more with another example of a circle. Okay, so here's a circle, and notice here, what's the opposite of minus 2? And you would say 2, all right? So I'm going to write this out. What's the opposite of minus 3? Oh, positive 2. Positive 3, sorry. Now that should be the center of the circle. Center at, and it should be 2, 3. Now you can see here, because I've put in the coordinates from Desmos, okay, that the center of the circle, see the first number is the x-axis, so it goes, is indeed, and the second number is the y-axis, is indeed 2, 3, okay? Now what radius does this have? It's not 4, it's the square root of 4, okay? So that means from here to here, and from here to here, from here to here, it must be 2. And it actually is. If you imagine that goes down there, that'll be 1. This will be 3, which it tells us already, okay? And the distance from there to there is 2, okay? So it works, okay? Now, how do we make it a function? Well, we have to do the same thing as we did in the first example. Sorry if you get dizzy, okay? If I square root, if I make y the subject of a circle and I square root it, the positive one will give me the top side of the semicircle. The negative one will give me the bottom side of the semicircle. So I'm going to do that with, I'm going to rewrite it here. If I go x squared, so I'm going to go back to the circle that we did in the previous page, equals, let's go with 9, okay? So I'm going to rearrange for y. Y squared equals 9 minus x squared. All I've done is taken away x squared from both sides, okay? Now I want to get y by itself, so I'm going to go y equals, and it's going to be plus or minus, because I've square rooted both sides, 9 minus x squared, okay? Now this one is still the same circle that we have here, okay? It's exactly the same. But if I just wrote y equals the positive 9 minus x squared, all it does, it gives us the top part of the semicircle, and it actually is a function because it crosses the vertical line test. Now also true, I'm going to draw a little straight line down here. Also true, if I wrote y equals minus this, it gives us not the whole circle, but just the bottom part of the semicircle, okay? And it also is a function that passes the vertical line test. All right, hopefully some of this makes sense. Really, with graphs, you just have to go in and play with it. Desmos will be a massive part of it, or you can do a table of values, but Desmos is a lot quicker to give us what graphs look like. If you just play around with Desmos and you go, what if I do this? What if I do that? And see important features of the graph, that will be of massive benefit to you. Anyway, that's the end of the lesson. Peace.